Hello students, in this session let us start the chapter solid state. Solid state. So you're already familiar with different states of matter. One among those is solid. Okay, in solids particles are closely packed. So now let's see the classification of solids. Solids can be mainly classified into two categories. First one is crystalline solid. First classification of solid is crystalline solid, and second type is amorphous solid. Amorphous solid. So these are two main classification of solid. One is crystalline solid, another one is amorphous solid. In crystalline solid, particles are regularly arranged. Regular arrangement of particles will be there. They will extend in all directions like this. See, you can see a regular arrangement of particles in all directions like this. One is below the another like this. Regular arrangement of particles will be there in case of crystalline solid, but in case of amorphous solid, there will be no regular arrangement. Irregularity will be there. Particles are arranged irregularly like this. So you cannot see any regularities in case of amorphous solid. Okay, so particles are irregularly arranged. Example for this amorphous solid is glass. Example is glass, and for crystalline solid you can take any example like NaCl or CaCl2 like this, MgCl2. They are all crystalline solids. Okay, yeah. Now let's see important differences between crystalline solid and amorphous solid. First, in crystalline solid and amorphous solid. Okay, so first property is in arrangement of particles. Just now I told arrangement. So in case of crystalline solid, how the particles are arranged? Particles are closely arranged, that will be in solid, and there is a regular arrangement. Long range order will be there. That means in long range particles are arranged in a particular order. Okay, so long range arrangement will be there in case of crystalline solid. Long range order will be there. Particles are arranged in long range order, but in case of amorphous solid, short range order will be there. It's not orderly arranged. Particles are not orderly arranged. That is short range order. And second property is about melting point. If you consider melting point, so these crystalline solids have definite melting point. These have definite melting point. That means if I take any crystalline solid, its melting point will be fixed. Like I'll take a crystalline solid X. If its melting point is 200 degrees Celsius, all its particles will melt at 200 degrees Celsius only. It's fixed. Its melting point is fixed. But if I consider any amorphous solid, it melts over a range of temperature. Like if I consider plastic is an example for amorphous solid. So it will melt between 200 degrees Celsius. I am giving example of this, 200 degrees Celsius to 250 degrees Celsius. There will be range of temperature. I cannot tell like at this particular temperature only it will melt. I cannot say like this for amorphous solid, but for crystalline solid I can say particular temperature, fixed temperature. So melting point will be fixed for crystalline solid. So amorphous solid will have they melts over range of temperature, over a range of temperature. They melt over a range of temperature. Okay, so this is the second difference. Now let us see about the heat of fusion. What is heat of fusion? So it's the temperature to convert solid to liquid, okay, temperature at which the crystal will convert from solid to liquid. So this also have definite heat of fusion, definite heat of fusion. That means heat of fusion is fixed at a particular temperature, they will convert from solid to liquid, but amorphous solid have indefinite heat of fusion, indefinite heat of fusion. And fourth is about their compressibility, compressibility. See, compressibility. So in case of crystalline solids, they are highly rigid. Crystalline solids are rigid and they are incompressible. They are rigid and incompressible because particles are arranged in a regular fashion like this. So there will be no space between particles, or there will be very less space between particles in case of crystalline solid. So they are rigid and incompressible. But this amorphous solid, I showed you earlier like this, the arrangement will be irregular. So there exists gap between particles. So they are compressible up to a small extent. Amorphous solid can be compressible up to a small extent, okay. They are compressible up to a small extent, not too much, up to a small extent, okay. Next, fifth one is cutting with a sharp edge, cutting with sharp edge, sharp edge tool. If I cut crystalline solid with a sharp edged tool, I will get a smooth plane. Smooth planes can be generated by cutting this crystalline solid with a sharp edge tool, okay. But in case of amorphous solid, I will get rough planes, rough or irregularities will appear, okay, rough planes will appear when you cut amorphous solid with the help of a sharp edge tool. Next is isotropy. Sixth property is isotropy and anisotropy. Sixth property is isotropy and anisotropy. So these crystalline solids and amorphous solids, crystalline solids are anisotropic in nature, anisotropic in nature, and amorphous solids are isotropic in nature. So what is this anisotropic and isotropic? In anisotropic means, so that properties will depend on direction, different they will show different properties in different directions, okay. Properties will vary in different direction. That means property is direction dependent in case of anisotropy, that is crystalline solids. They are anisotropic in nature. That means their direction properties are direction dependent, okay. So anisotropy means properties are direction independent. Like see, what will happen due to irregularities, the properties will get averaged. You will take average of properties due to these irregularities in anisotropic solids. So because of this average, you will get same property in every direction. That is called as isotropic nature, okay. So properties are direction independent. You will not consider, properties will be same in every direction, but in case of crystalline solid, properties will not be equal in every direction, okay. Next is seventh property is symmetry. Symmetry. So these are crystalline solids are symmetric in nature. These are symmetric. That means they will possess plane of symmetry, but amorphous solid do not possess symmetry. They do not possess symmetry. Anisotropic solids will not have plane of symmetry and all, okay. Next, eighth one is interfacial angles. interfacial angles. See, crystalline solid possess interfacial angle. They possess interfacial angle. They possess interfacial angle, but these amorphous solids will not possess interfacial angle. These amorphous solids are also called as pseudo solids. Pseudo solids, because see, amorphous solids are not true solids. They are called pseudo solids or super cooled liquids. So they are called amorphous solids are called as pseudo solids or super cooled liquids. Okay, so in this chapter you are going to study only about crystalline solids, because amorphous solids are not true solids. You are going to study only about crystalline solids. Okay, now let us see different types of crystalline solids based on force of attraction among constituent particles. These crystalline solids are mainly classified into 4 types. First one among those is molecular solid. First one among those is molecular solid. So this is first type of crystalline solid. See, this molecular solid can be further classified into 3 types. First one is non-polar, and second one is polar molecular solid, and third one is hydrogen bonded molecular solid. Hydrogen bonded molecular solids. These are three main classifications of molecular solids. Okay, first one is non-polar, second one is polar, and third one is hydrogen bonded molecular solids. In case of non-polar solids, there will be no charge. No charge. Non-polar means no charge will be there on molecule. Charge separation will not be there. So there is no charge separation. Then how they are attached? How the constituent particles are attached? Through London forces. So London forces will be there between particles. Okay, London forces. So particles or atoms are held together by London forces. Example for this non-polar molecular solid is H2, I2 or CCl4, etc. These are all examples for non-polar molecular solid. They are soft in nature. Non-polar molecular solids are soft in nature, and they are insulators. They will not conduct electricity. Insulators. They behave as insulators, and they have very low melting point. Melting point is very low for non-polar molecular solids. Now let's see about polar molecular solids. Here polar means charge separation will be there. That means dipoles will be induced, different poles will be induced. So their constituent particles are held together by dipole-dipole interaction. Dipole-dipole interaction will be there. Dipole-dipole interaction will be there. Example is HCl, SO2, etc. You can take any example for this. So these polar molecular solids are also soft in nature, and they also act as insulators. They will not conduct electricity. They are insulators, and they have low melting point. The melting point is low. For non-polar molecular solids, it's very low. For polar molecular solids, it's low. Okay. Next is hydrogen bonded. As the name indicates, particles are held together by hydrogen bond. Hydrogen bond holds different particles together. Example is H2O. That means ice. I will consider ice as an example for this. These are also insulators. These are also insulators, and they have low melting point. They also have low melting point. Okay, these are different types of molecular solids. Okay, next, second type of crystalline solid is ionic solid. Second type is ionic solid. This is second type of crystalline solid, that is ionic solid. So here ions are constituent particles. Constituent particles are ions. In case of molecular solids, constituent particles are molecules. Here constituent particles are ions. Okay. So here since they are ions, they will be held together by electrostatic force of attraction. Electrostatic force of attraction holds different constituent particles or ions together. Okay. Example is NaCl, MgO, ZnS, etc. So these are all examples for ionic solids. So ionic solids are usually hard. You have seen this NaCl in your kitchen. So it will be hard and brittle. They are hard and brittle. Ionic solids are hard and brittle in nature. They conduct electricity only in aqueous solutions. So these ionic solids will not conduct electricity in solid state. They act as insulators in solid state, but they conduct in aqueous state. Okay, due to free electrons, when they are when they are converted into aqueous state, electrons are set free and they will conduct electricity. They act as conductors in aqueous state, only in aqueous state, not in solid state. In solid state they act as insulators and they have high melting point. Melting point will be very high for ionic solids. Next, third classification of crystalline solid is metallic solid. Third classification is metallic solid. This is third classification of crystalline solid. So here in case of metallic solids, positive charge or positive ions are delocalized in, or positive ion will be present in a sea of delocalized electrons. So that means positive ions are surrounded by electrons, too many electrons in a sea of delocalized electrons. Positive charge will be there. Okay, so here constituent particles or this positive or negative charges are held together by metallic bonding. Metallic bond holds these constituent particles, positive and negative ions, together. Example for metallic solid is iron or magnesium or copper, etc. So these metallic solids are hard, malleable and ductile. So these are hard, malleable and ductile. They are metals are good conductors of heat and electricity. They are very good conductors. So metallic solids are good conductors of heat and electricity and they have very high melting point. Melting point is very high. They possess high melting point. This is about metallic solid. And next, fourth classification of crystalline solid is covalent or network solid. Covalent or network solid. Covalent or network solid. So here constituent particles are atoms. Atoms are constituent particles in case of covalent or network solid. Atoms are held together by covalent bond. Covalent bond holds constituent particle, that is atoms together. Covalent bond holds different constituent particles together. Example is quartz at SiO2. SiO2 is an example for covalent or network solid. Remember this is one of the very important question. Quartz, SiO2, quartz, and silicon carbide, diamond, then Aluminium nitride, ALN. These are all examples for covalent or network solid, and this is graphite. C is for graphite. So this diamond and graphite are different allotropic forms of carbon. So here I write this is for diamond. They are hard. Covalent solids are hard except graphite. Graphite will be smooth, okay, and they are all insulators. They will not conduct electricity. They are all insulators. They will not conduct electricity, and they have very high melting point. Very high melting point. Melting point will be very high for covalent or network solids, okay. So this is different classification of crystalline solid. Next is crystal lattice. Crystal lattice. Crystal lattice. See, crystals will, or your solids will consist of atoms, ions or molecules, okay. So there will be regular arrangement of these atoms, ions or molecules inside the crystalline solid is called crystalline lattice. What is crystalline lattice? It is a regular arrangement of constituent particles, like atoms, ions or molecules, okay. Constituent particles, regular arrangement of constituent particles inside the crystalline solid. Remember this, inside crystalline solid, inside crystalline solid. For example, if I consider a wall, so walls are made by bricks, right? See, one brick will be kept beside another like this. Bricks are kept one after the another and one over the other like this. So crystal lattice is similar to this. If you consider these single bricks as constituent particles, so this whole arrangement of different bricks represent your crystal lattice. Your whole wall represent crystal lattice in which the constituent particles are arranged like this. In orderly arrangement will be there. Regular arrangement of constituent particles will be there. So in case of wall also, bricks are arranged like this in a regular way. So if you consider these as constituent particles like atoms, ions or molecules, this represents, whole arrangement represents crystalline lattice, okay. Here each of this is called as that is the smallest part is called as unit cell. This smallest part is called as unit cell. So this same type will repeat in every direction to form whole crystal lattice, okay. So unit cell is the smallest part of the lattice which repeats in all direction to form whole lattice. This single brick is called as unit cell. So you will keep same type of brick one after the other in all direction to make whole wall. In the same way, in case of your crystal lattice also, unit cell will unit cell will extend in or repeat in every direction to form whole lattice, okay. Next is three-dimensional unit cell. See, you can represent unit cell in three-dimensional. Let us see how to represent and what are the parameters. 3D unit cell, three-dimensional unit cell, okay. I'll write a cube like this, okay. It possesses different edges. Let me name them as A, B and C. This angle which is opposite to this A, edge A is called as alpha. This is edge A, angle opposite to A is alpha. Angle opposite to edge B is beta, and angle opposite to edge C is gamma. Okay, so here A, B, C are edge length and alpha, beta, gamma are interfacial angles. So alpha will be opposite to edge A, beta will be opposite to edge B, and gamma will be opposite to edge C. Okay, there are 7 different types of unit cell. How many unit cells are there? 7 different types. First one is cubic unit cell. Cubic unit cell. There are 7 different 7 types of unit cells are there. 7 types of unit cell. See, first one among those is cubic unit cell. In cubic unit cell, A will be equal to B, which will be equal to C. That means all the edges will be equal, and alpha will be equal to beta, which is equal to gamma, which is equal to 90 degree. All the interfacial angles will be equal to 90 degree. And second type of unit cell is tetragonal. First one is cubic, second one is tetragonal. Here A will be equal to B, which is not equal to C. A will be equal to C, but they will not be equal to, sorry, A will be equal to B, which is not equal to C. And here alpha is equal to beta is equal to gamma, which is equal to 90 degree. And third one is orthorhombic. Orthorhombic. Here A will not be equal to B, will not be equal to C. All edge lengths will be different, and alpha will be equal to beta, will be equal to gamma, which is equal to 90 degree. All the angles will be equal to 90 degree. And fourth one is trigonal. This unit cell is also called as rhombohedral. Okay, in case of rhombohedral, A will be equal to B, which will be equal to C. And if you come to interfacial angle, alpha will be equal to beta, will be equal to gamma, but it will not be equal to 90 degree. Okay, all the angles are equal, but they will not be equal to 90 degree. And next is fifth one, that is hexagonal unit cell. Here A is equal to B, which is not equal to C. Okay, A will be equal to B, which is not equal to C. So here alpha is equal to beta is equal to 90 degree, and gamma is equal to 120 degree. Angle gamma will be different. Next, sixth one is monoclinic. Here A will not be equal to B, will not be equal to C, and interfacial angle alpha will be equal to gamma, which will be equal to 90 degree, and beta will not be equal to 90 degree. Okay, beta will be different from 90 degree. And seventh, last type of unit cell is triclinic. Unit cell. Here A is not equal to B, which is not equal to C, and alpha is not equal to beta, not equal to gamma, which is not equal to 90 degree. Okay, so these are different 7 types of unit cell. Okay, now see, there are 7 types of unit cell, or 7 types of crystal system. You can say 7 types of crystal system. 7 types of crystal system, and 4 subtypes are there for each crystal system. Each type of crystal system, there are 4 subtypes. Therefore, there are 7 into 4, which is equal to 28 possible Bravais lattices are there. Bravais lattices. Bravais lattices are there. There are 28 Bravais lattices till now only 14 Bravais lattices are found. Okay, I mean they are proven. 14 Bravais lattices are found to exist. There are only 14 Bravais, existence of only 14 Bravais lattices are there till now. Okay, let us see first one, that is simple. Let us see 4 subtypes of this. Okay, first one among those is simple cubic. First one is simple cubic. Simple cubic unit cell. See here, in case of simple cubic, particles will be arranged only at corners. You can see particles only at corners of the cube. Here one particle will be there. There are 8 corners, and at each corner atom will be there. Constant particles will be present only at corners. See, if you find number of atoms per unit cell, this is one unit cell. In the same way, unit cell will extend in different direction. It will extend in different direction to form whole lattice, right? So, what is the number of atom present per unit cell? Number of atoms present in a single unit cell. See, unit cells are arranged one after the other. Consider this, I'll show in a 2 dimension. This is one layer. They are arranged like this. This I'm talking only about upper surface. Okay, so here one particle is shared between 8 unit cell. One particle at one corner. Consider this as one corner. Here, after this, one more will come here. One more layer will come here, one more layer will come front, and above this layer one more layer will come. Okay, total this unit particle will be shared, or this atom will be shared between 8 unit cell. So, that indicates one particle will be shared, one particle will be shared between 8 unit cell into how many corners are there, how many particles are there in a unit cell? 8 particles, 8 corners will be there. So, 8 particles, and each particle will represent 1 by 8. It will represent 1 by 8 to the unit cell. That means, one particle will be shared between 8 unit cell, which is equal to 1. So, simple number of particles in simple cubic unit cell is 1. Remember this, this is very important. For simple cubic, Z is equal to 1. Number of particle per unit cell for simple cubic is 1. Okay, and second type is body centered. Body centered. Body centered unit cell. This is also called, it is represented as BCC. Body centered cubic unit cell. Okay, so it is here particles will be there at each corner and at a body center. Each corner contains atom, and one atom will be present at body center. Center of the cube, one atom will be there. This is body centered cubic unit cell. How will you calculate number of atoms in body centered cubic unit cell? 8 corner atoms are there, and each corner atom contribute 1 by 8 to unit cell. Okay, corner atom is over, plus an atom is present at body center, at center of the cube. This is not shared between any other atoms because it is present inside the cube. So, one atom is present inside the cube. So, it total its contribution is only towards this unit cell. This is not shared, this central atom is not shared between any other unit cell. So, its whole contribution is for this unit cell only. Therefore, number of particles per unit cell in body centered cubic unit cell is 2. So, that means Z is equal to 2 for body centered cubic unit cell. Okay. Next one is third type of third subtype is FCC, that is face centered cubic unit cell. Here particles will be present at each corner and on the faces of the cube, on each face, on all the faces of the cube. First, particles will be there on at each corner, okay, and you can see the particles at each faces, 1, 2, front, back, left, right. On all the faces you can see particles. See, let me consider this face. Another unit cell will be there at this side also, right? So this particle, the particle which, or the atom at one face is shared between 2 unit cell. So how will you find number of particles? 8 corner atoms into contribution is 1/8 plus. See how many atoms are there at face? 6 faces are there. So 6 atoms and contribution of each atom. That means one atom will be shared between 2 unit cell. One atom at the face will be shared between 2 unit cell. So total will be 3. Oh, sorry, total will be 4. So number of atoms per unit cell in FCC is 4, that is Z is equal to 4 for FCC. Okay. Next fourth type is end centered. End centered. End centered unit cell. Here particles will be there at each corner. Each corner contains particles and particles will be present at opposite faces, only at 2 opposite faces. See, if one particle is present here, another particle will be present here. Okay, it contains particles at opposite faces. So corner atoms, 8 corner atoms, each will contribute 1/8 to unit cell plus 2 atoms at face, and facial atoms will contribute 1/2 to unit cell. So total is 2. So Z is equal to 2 for end centered cubic unit cell. Okay. So this is about subtypes of unit cell. Next one is packing fraction. Packing fraction. Packing fraction. What is this packing fraction? So packing fraction is nothing but fraction of volume occupied by spheres in unit cell. That means in a unit cell, some portion will be occupied by atoms. Not all 100% spaces inside your unit cell will be covered with atoms. There will be some spaces also. So here you will calculate how much of space is occupied by your constituent particles inside your unit cell. Okay. So packing fraction is given by the formula volume of spheres in one unit cell. Volume of spheres in one unit cell divided by volume of cube. Volume of cube. See, volume of one sphere is given by 4/3 pi r cube. 4/3 pi r cube. That is volume of one atom or one sphere in unit cell, and you have to multiply it by total number of atoms or total number of particles per unit cell, that is Z, divided by volume of cube. Volume of cube is A cube. This is the formula to find packing fraction. Packing fraction of a unit cell can be found by the formula Z into 4/3 pi r cube by A cube. This is one of the very important formula. Now let us see packing fraction of different unit cell. First among those is simple cubic unit cell. Simple cubic. So I am not going to calculate packing fraction or packing efficiency. I will make a chart of this. You have to remember all the values. Okay, this is very important. So next, relation between edge length A and radius of particle R. Third one is number of atoms Z. Fourth one is packing fraction. Okay, this is structure. First column is structure. Okay. Simple cubic. Here relation between A and R is A is equal to 2R. Number of particles present in simple cubic is 1. Its packing fraction is pi by 6, which is equal to 0.52. You can write packing efficiency. That you will get packing efficiency by multiplying packing fraction by 100, that is 52%. Packing efficiency is 52% for simple cubic. Next, second one is BCC, body centered cubic unit cell. Here relation between A and R. A means edge length, R means radius of spheres present in unit cell. Okay, so here I'll get the relation A is equal to 4R by root 3. Number of particles for BCC is 2. 2 particles will be present in a single body centered cubic unit cell, and packing fraction is root 3 pi by 8. Remember this, root 3 pi by 8, which is equal to 0.68, which is equal to 68%. Packing efficiency is 68%. Next is FCC, face centered cubic unit cell. Here A is equal to 4R by root 2 and number of particles present in FCC is 4 and its packing fraction is root 2 pi by 6, which is equal to 0.74. Packing efficiency is 74%. Remember all this. This is packing fraction is very important. Remember all these values. Okay, you have to remember even pi by 6, root 3, pi by 8, these values also. Don't remember only this 0.74, 0.68 and 0.52. Only don't remember only these values. These values are also important. Okay. Yeah. Next topic is density of cubic crystal. Density of cubic crystal. See, you will get some numerical problems based on this density. So the formula to calculate density is rho is equal to m into z divided by a cube into Na, where a cube is volume, that is edge length whole cube, z is number of particles, Avogadro number, Na is Avogadro number, m is molar mass. If rho is in gram per cm cube, if you have to represent a density in gram per cm cube, then your molar mass should be in gram per mole and edge length should be in centimeter. Then only if your molar mass is in gram per mole and edge length is in centimeter, you can represent rho in gram per cm cube. If you have to represent rho, that is density, in kg per meter cube, then your molar mass will be in kg per mole and your edge length will be in meter. Okay. Yeah. Next is packing in solids. Packing in solids. Next topic is packing in solids. See, first among this is square packing. Square close packing. Square close packing. So here first one is one dimensional. I'll write one dimensional square close packing. Here particles will be arranged like this, one after the other in a one direction, only in one direction, like this. Only in a single line all the particles are arranged. Here what is the coordination number? Coordination number. I'll consider this. This atom is surrounded by 2 atoms. It is attached to 2 atoms. So its coordination number is 2. In case of one dimensional close packing, coordination number is 2. Next is 2 dimensional close packing. 2 dimensional close packing means particles will be arranged in 2 dimension like this, and next one will be one below the another like this, and next layer will come after this like this. This is 2 dimensional close packing. This is also called as AAA type arrangement. Similar type of layers will be there, AAA type arrangement. Okay, here what will be the, what is the coordination number? Coordination number for 2 dimensional close packing. See, I'll consider this atom. This atom, it is surrounded by, it is attached to 1, 2, 3, 4. 4 different atoms. See, there is no link between these 2 atoms. Okay, only it is attached to 4 other atoms. So coordination number in case of 2 dimensional square close packing is 4. Okay, this is square close packing is one type, and second type is, next type is hexagonal close packing. Hexagonal close packing. Hexagonal close packing. So first is 2 dimensional hexagonal close packing. Here one layer will be like this. In next layer, particles will come in between these 2 atoms like this. See, like this, particles will come in between these 2. Next layer will be like this. They will present in gap between 2 particles. Now see, I'll draw like this. It looks like a hexagon, right? So this type of arrangement is called as hexagonal close packing. What is the coordination number for this atom? It is attached, directly attached to 6 different atoms. So here coordination number is 6. Coordination number is 6. This type of arrangement is also called as AB type arrangement. See, these particles are same. This layer and this layer are same, and this layer is different. Okay, AB type arrangement. In 2 dimensional close packing, that is hexagonal close packing, you can see AB type arrangement. Next is 3 dimensional hexagonal close packing, that is 3 dimensional in square close packing. How will you find 3 dimension in square close packing? Here AA type arrangement will be there. You will arrange the particles like this and it will go like this. See, it is difficult to draw. I will try to write it. All of you, I think all of you have seen Rubik cube. It's like that only. Okay, like this. One layer will be there above the another. This is hexagon, this is square close packing in 3 dimension. Okay, this is AA type arrangement. Here coordination number is 6. Remember this, coordination number is 6. And in hexagonal close packing in 3 dimension, 3-dimensional hexagonal close packing, remember this, 3-dimensional hexagonal close packing, coordination number will be 12. This is important. Coordination number for hexagonal close packing in 3 dimension is 12. Okay, next is voids. Next is about voids. What are voids? So they are nothing but gaps in unit cell, empty spaces present in unit cell. See, most efficient packing is only 74%. That is in FCC. In FCC, I have told you packing efficiency is 74%. That is in case of CCP and HCP, it is packing efficiency is 74%. Except this 74%, other empty spaces which are present are called as voids. Empty spaces. Empty spaces are called as voids. So this voids, size of the voids can be represented by radius ratio. They can be represented by radius ratio, that is r by r. Now there are different types of voids. First one is trigonal void. Trigonal void. Now this trigonal void is surrounded by three spheres. Surrounded by three spheres like this. One sphere, second one and third one. This, you can see a gap here. This gap is nothing but trigonal void. Trigonal void is surrounded by three spheres and its coordination number is 3. Its coordination number is 3. Next is tetrahedral voids. Tetrahedral void. So it is surrounded by 4 spheres like this. This is first sphere, second sphere and one will be behind, third sphere. So you can see a gap in between this one like this, and I'll place one more sphere from the top like this. I'll keep it from the top. So this void is surrounded by 4 spheres. This type of void is called as tetrahedral voids. In tetrahedral voids, coordination number is 4. Coordination number is 4. See, it will be, this tetrahedral void will be present in each body diagonal. Each body diagonal. For example, if I write a square, I'll write a cube. In cube, I'll write body diagonal. Body diagonal means from this point to this point. I can draw one body diagonal. I'll divide this body diagonal into 4 equal parts. 1, 2, 3, 4. I'll divide this into 4 equal parts. I can see tetrahedral voids in this 1/4 arrangement. I can see tetrahedral voids, 2 tetrahedral voids in a one single diagonal, body diagonal. Okay. In the same way, I can write 4 different body diagonals, right? So there will be 8 tetrahedral voids. Each body diagonal contains 2 tetrahedral voids. I can draw 4 different body diagonals for this cube. So it contains 8 tetrahedral voids. In case of your hexagonal close packing, your Z is equal to 6, right? So number of tetrahedral voids will be 12. For your FCC, in case of face centered cubic, in case of FCC, Z is equal to 4. For FCC, Z is equal to 4 and number of tetrahedral voids is equal to 8. That means tetrahedral voids can be, remember this is very important. Tetrahedral voids is number of tetrahedral voids is equal to 2 into number of particles, that is 2 into Z. Remember this formula, number of tetrahedral voids is equal to 2 into Z. Z is number of particles present in unit cell. This is very important formula. Number of tetrahedral voids is equal to 2 into number of particles present in unit cell. Now let us see, tetrahedral void is over. Next is octahedral void. Octahedral void. So here coordination number is 6. Coordination number is 6. Like the void is surrounded by 6 atoms. I will try to show this. 1, 2, 3. Okay, here one gap will be there. Another will be like this. Second layer, 1, 2 and 3. A gap will be there in between these two. If I place these 2 layers, this gap in between these 2 is called as octahedral void. If I place this layer over this layer, The void created in between these two is called as octahedral void. This will be present at body center. So this void will be present at body center. So number of octahedral void in a unit cell is given by number of octahedral voids is equal to Z. Remember this one also. Always number of octahedral voids is equal to number of particles present per unit cell, and number of tetrahedral voids is equal to 2 into number of particles present in unit cell. Okay. So this is about voids. Next is imperfection in solids. Imperfection in solids. Imperfection in solids. So these imperfections or defects can be of two types. First one is due to vacancies, and second one is due to interstitial site. Interstitial site. So imperfections in solid can be due to two reasons. First one is due to vacancies, second one is due to occupying of interstitial sites by different ions. So vacancies means like in a regular arrangement, one atom or ion will be missed from its site. They will create vacancy like this. Here it will be mixed. That means missing of ion or constituent particle will take place, which creates vacancy. And second one is interstitial site, moving of constituent particle to interstitial site like this. See, there will be regular arrangement and one particle will be present at interstitial site. These are two reasons for imperfection in solids. Okay. So there are two types of imperfections. First one is stoichiometric defect and second one is non-stoichiometric defect. First let us see about stoichiometric defect. Stoichiometric defect. Imperfection in solids can be mainly classified into two types. First one is stoichiometric defect. Here number of cations will be always equal to number of anions. Neutrality will be maintained. First stoichiometric defect is Schottky defect. Schottky defect. So what is Schottky defect? So here number of missing cations and anions are equal. Equal number of cations and anions will they will create vacancies in unit cell. Okay. Equal number of cation and anions will be missed from lattice site. Missing of equal number of cations and anions will take place in case of Schottky defect. Okay. Here density will decrease because missing of cations and anions will leave the lattice. They will leave the lattice and they will create vacancies in their position. So then what happened to density? Density decreases because of missing of cations and anions. If one cation leaves this lattice, one anion will also automatically leave the lattice. Equal number of cation and anion missing will take place. So this is shown by some crystals which have in which cation and anion size are almost equal. So to show Schottky defect, size of cation and anion should be equal. Example is NaCl, KCl, AgBr etc. Okay, this in all these cases size of cation and all anion are almost equal. So Schottky defect decreases density of the crystal, equal number of cations and anions will miss from lattice site. And second stoichiometric defect is Frankel defect. Frankel defect. So here smaller ion will move into interstitial site. Smaller ion. So which one will be smaller? Smaller ion will move into interstitial site. So there will be no missing of ions. So density will not change. Ion will move into smaller ion. Smaller ion will move into interstitial site. Interstitial site. Smaller ion will move into interstitial site. So there will be no change in density. No change in density, because there will be no missing of cations and anions in this case. Since there is no missing of cation and anion, density will not change. No change in density. Density will not change in this case. Okay. Yeah. Next is to show this Frankel defect, they should have different cations and anions should have different size. Size difference between cations and anions will show Frankel defect. For example, ZnS, AgCl, AgBr, etc. AgBr shows Frankel defect as well as Schottky defect. These are some of the stoichiometric defect. Next is non-stoichiometric defect. Non-stoichiometric defect. Non-stoichiometric defect. So there are two types. One is metal excess defect, and another one is metal deficient defect, metal deficiency defect. So in case of metal excess defect, number of metal cations are more than number of anions. Number of metal cations are more. Metal cations are more than metal anions. Okay, number of metal cations are more than metal anions. This can be produced due to two reasons. There are two reasons for greater number of cations in metal. So first one is anionic vacancies, due to anionic vacancy. First reason is due to anionic vacancy. That means, see, if anions move from lattice, or if anions move out of metal, they will create more number of cations. Number of cations increases because anions will leave their site. So this is one reason why number of cations increases in metals. Okay, so this anions which left the lattice will produce a center called F center. So this F center will impart color to crystal. So this F center is reason for imparting of color to crystal. Remember this is important. Okay, next, second is due to extra cation. Due to extra cation. So this is because cations occupy interstitial sites and electron is present in another interstitial site. So in one interstitial site extra cation will come and sit, and another interstitial site, instead of anion, electron will come and sit. Okay, this is reason for extra number of cations in metal. So these are metal access defect. Next is metal deficiency defect. So this if defect occurs when metal shows variable valencies. If metal shows variable valency, then metal deficiency defect will occur. For example, in FeO. So here the Fe will vary from 0.93 to 0.96. This is due to two different oxidation state of iron, Fe+3. Okay, different of variable valency is reason for metal deficiency defect. Okay, this is about defects. Next is electrical properties. Next, last topic is electrical properties. First is conductors. What are conductors? Conductors, they conduct electricity. So why they conduct electricity easily? In metals there are two bands. One is conduction band, and second one is valence band. There exists two different bands in conductors or in metals. Okay, conduction band means the band which contains electron. Okay, band which outermost band which contain electron is called as conduction band, and the lowest energy band which will not contain any electron is called as valence band. Okay, in case of conductors, the distance between conduction and valence band is very less, or you can consider them as overlapped. Conduction band, this is conduction band and this is valence band. Conduction band and valence band will overlap. So electron can easily jump from conduction band to valence band. Valence band will be vacant. Conduction band can electron in conduction band can easily move into valence band. So easy movement of electron between conduction band and valence band is the reason for conduction of electricity between metals or in metals. Okay, so what is the reason for conduction of electricity? That is due to overlapping of conduction band and valence band. In case of metals, there will be very less gap between conduction band and valence band, or conduction band will overlap with valence band so that electron can easily move and it can transfer electricity. Okay, next is insulators. What are insulators? They will not conduct electricity. Insulators, that means electron movement will not be there. When movement will not be there? When conduction band, the distance between conduction band and valence band is very high. Conduction band and valence band, when distance between these two, conduction band and valence band, is very high, then electron cannot jump from conduction band to valence band. So this type of substances acts as insulators. Okay, so this type of substances acts as insulators, in which conduction band and difference between conduction band and valence band is very high. Next one is semiconductor. Third type is semiconductors. Semiconductors. So here there exists a small gap between conduction band and valence band. Conduction band and valence band, there exists a small gap. If I increase the temperature, at lower temperature they act as insulators. At higher temperature, if I increase the temperature, what will happen? Electron will gain energy and it will jump into valence band. It's easy for electron to jump into valence band at some higher temperature. So because of this, they conduct electricity. At lower temperature, they act as insulator. And at higher temperature, they act as insulators. Okay, for example, silicon, and germanium. These are examples for semiconductor. I can enhance the conductivity of semiconductor by adding some impurities. These impurities are called as dopants, and this process is called as doping. Okay, I can enhance the conductivity of semiconductors by adding some impurities called dopants. So this process is called as doping. See, there are two types of semiconductor. One is p-type semiconductor, and second one is n-type semiconductor. P-type semiconductor and n-type semiconductor. If I dope 14th group element with 13th group element, then I will get p-type semiconductor. If I dope 14th group element with 15th group element, then I will get n-type semiconductor. In n-type semiconductor, electrons are charge carriers. In p-type semiconductor, holes are charge carriers. Okay, that means, so in case of 14th group element, number of outermost electron will be 4. Let me consider A. Okay, A as one of the element which is present in 14th group. Now I'll add dopant, that is impurity, from 15th group, one element from 15th group. Number outer valence electron in 15th group is 5. I'll consider it as B. It contains 5 electrons. Okay, so one electron among this set free, other will bond with other electrons in other atoms. This will be set free, which increases the conductivity. That means electrons will be more. So these extra electrons acts as charge carriers in n-type. In case of p-type, 14th group element, that means which contain 4 electron, will be doped with 13th group which contains only 3 electrons. One place will be left vacant. So this acts as charge carrier. That means electron will jump from one another atom to this vacant space. So it looks like hole is moving. This hole is moving. So holes acts as charge carriers in p-type semiconductor. That completes this chapter. If you have any doubts, you can contact me by any time. Thank you.